Hey everyone, Professor Michael Scanlan here. So in our STEAM series, I wanted to talk to you about gravity. Gravity, the force that makes things fall. What's so special about gravity? It just keeps me on the earth, right? I wish I could say that we're all it does. You know what, I'm glad that's not all it does. Gravity is responsible for a lot of things. And it's very different than you and I tend to think about in our everyday, just go about our day lives. So, Isaac Newton, number one, did not get hit on the head with an apple. What did he do with gravity? Well, he discovered gravity. No, the first person to trip and fall discovered gravity. We knew things fell. Isaac Newton was able to show that the force that pulls things to the ground whenever I drop them, if I were to drop this ball bearing, it hits the table, gravity pulls it down. The force keeping me anchored to the stool, keeping us on the earth, is gravity. That force and the force that keeps the earth going around the sun, the moon going around the earth, it's the same thing. Newton was able to show that gravity is not just what pulls things to the earth, but rather it's a universal thing. Okay, it's what keeps the planets going around the sun, the moon's going around the planets, etc. Newton was able to show that gravity is everywhere, that there's nowhere you can go, technically, where there is no gravity. Gravity's limit is infinity. That's where gravity goes to zero, is when you're infinitely far from some mass. Well, I'm never infinitely far from anything. So no matter where I go, there's gravity. The problem with Newton was, and his theory, okay, for lack of a better term for it, was he couldn't explain what gravity is. He could just talk about how it behaved. Now, Isaac Newton lived in the 1600s. We have to fast forward a few centuries into 1915 with Albert Einstein, who was able to show what gravity actually is. Now, to understand that, we have to rewind. We're bouncing back and forth in the timeline here. We have to rewind to 1905 with Einstein's special theory of relativity. In it, he states, basically, nothing can travel faster than the speed of light. A lot of other stuff goes in with that, but that's the part that I want to focus on. And so, according to that, nothing, no information, no force, nothing can travel faster than the speed of light in a vacuum. In terms of Isaac Newton, if the sun were to mysteriously disappear, poof, right? It takes just over 8 minutes, about 8 1/3 minutes, for light to get from the sun to us here on Earth. And so the sun, poof, disappears. It would take 8 1/3 minutes for us to realize that, because the last light from the sun is still traveling after the sun disappears, and then it gets to us and we go, oh, hey, what happened to the sun? According to Newton, as soon as that poof happened, yeah, the light takes time to get to us and for us to realize that there's no more sun. But the gravity between the earth and the sun would be instantly dissolved. Boom. So, in other words, the force of gravity would travel faster than the speed of light in a vacuum. Einstein couldn't handle that. That's not what he discovered. 10 years later, we get to the general theory of relativity, or general relativity. And we see that he's able to show what gravity is, and he actually shows that gravity travels at the speed of light in a vacuum. So if we go back to our sun scenario, right, and let's say the sun just poof disappears, it would take 8 1/3 minutes for the light to get to us and us to realize the sun is gone. We would continue orbiting as though the sun were there for that same amount of time. And once the gravity force shockwave really gets to us, then we would fly off in a straight line according to our inertia. Topic for another day. With that, Einstein's able to show that space and time, what he calls spacetime, is manipulated in one sense by mass. The more mass something has, the more it manipulates space-time around it. And you can think of it as a trampoline. Okay, this is how scientists try to communicate this. Think of it as a trampoline, a really big trampoline, right? I put a bowling ball in the trampoline. That trampoline is going to dip. If I put something much heavier than the bowling ball, take the bowling ball away, put something much heavier, it's going to dip more. So kind of sort of the same thing. The more mass something has, the more space and time warp. So here's something that you can try at home and kind of get a qualitative feel for this. I've got some paper that I've cut into circles. Actually, I didn't cut these into circles, they came in circles. But get some paper and cut it into circles, and then make different shaped cones out of the paper. So I've got a shallow one here, a steeper one here, a much steeper one here, okay? And I've got a ball bearing. Now, if I take this ball bearing and I just stay put, I'm gonna have to hold my space-time here. I allow it to orbit, it's going to go around and around and around and around. I'm gonna bring the camera close so you can see what's going on here. So if I hold my space-time, let the marble go around, this is full of friction, so it does eventually stop, is an orbit, right? I have an object following the curvature. Now you notice it's not following it. I lost my planet. Okay, I'm back with my planet. It's not following necessarily in a circle, but rather in an ellipse, in an elliptical orbit. What if I put in a steeper curvature? That is, I have a bigger mass here. Well, I'm gonna get a faster orbit. This thing is steeper, right? And the same thing here, I don't think it's gonna work very well here, but we'll give it a shot anyway. Yeah, just kind of plunk down. What I wanna show with the steepness isn't how fast it orbits, because that's not really necessarily a correlation here. I wanna show something else. Now, imagine I'm holding this, all right, and I have this in the center. I want to flick it, right? And I want to try to get it out of this paper, off of this paper. That wasn't too hard. I'm gonna grab my next one. And I want you to try this. Get your marble, your ball bearing, whatever, put it in the next steepest cone, and try to flick it with the same force. And you notice it doesn't quite make it out. To make it out, I've got to make it go harder. Put it in this one. Good luck with this one. You're gonna have to hit it really hard to get it out. What's happening here? Look at me when I'm talking to you. What's happening is the steeper these curves, the more difficult it is for the ball bearing to get out. That's the relationship I want you to see with these activities, with these pieces of paper. It's called escape velocity. Now, you're not really escaping gravity because, as we just said, gravity is everywhere, you can't get away from it, right? Escape velocity is the speed something needs to go to leave an object and never come back, okay? An orbit is gonna continuously go around it. Escape it is gonna leave it and not come back. There's still a force there. The force just isn't strong enough to pull it back. So notice the steeper the curve, the steeper the cone, the more difficult it was to get it out. The faster this thing had to go to escape. Now let's put that in terms of gravity. Let's say I have something that's very high mass. In order to escape something that's very high mass, I'm gonna have to go really, really fast. To escape something that's low mass, that doesn't cause much of a bend here, I'm not gonna have to go that fast. Nothing can travel faster than the speed of light, right? In a vacuum. What happens if I have an object so massive that the escape velocity, the speed needed to move away from this thing, is the speed of light? Think about that. The steeper these things get, the faster I have to move this to get it out. Imagine one so steep, I have to move this the speed of light to get it out. What have I just made? A black hole. And that's what a black hole is. And that's why light can't escape it. Nothing can escape it, because nothing can travel faster than the speed of light. And that's the requirement to escape a black hole, is to travel faster than the speed of light. So it's catch-22, you're stuck. Hey, I know this video was a little bit longer than usual, but I hope you found it interesting. If you can't tell, this is kind of one of my favorite topics. I'll see you in the next video. Stay safe, everybody.